Section 31 is on what we call linear approximations. So there's a pretty complicated equation that is in most calculus textbooks. We're not going to learn the complicated equation. We're just going to use some logic skills here. We're going to talk about what we know. We're just going to think about why this is true. Okay, so with linear approximations, all we're doing is we're finding the equation of a tangent line. Do you guys remember me giving you instructions like that? Find the equation of a tangent line through this point. Okay, what were the two things I needed when I was finding the equation of a tangent line? I need the first derivative to find what on the line? The slope. And then I need what? A point. Okay, once I have the slope and a point, I do my y minus y1 equals m times x minus x1, and I have the equation of a tangent line, right? Do we all know how to do that? Yeah, that's what all this section is. Okay, very, very easy. So here's what we're going to do. So we're going to basically have these curves. So we're going to have something like the cube root of x. And I'm going to ask you to find things like the cube root of 7.8. Okay. I don't know what the cube root of 7.8 is. I can make a guess. What do you guys think it's close to? 2. Is it above 2 or smaller than 2? It's smaller because it's smaller than 8, right? The cube root of 8, which is 2. So I can make some little rough guesses for this. Maybe, I don't know. That seems too small for me. I think it's probably going to be more like 1.9 something. All right, so I'm not sure. So what we can do, and what they used to do before there were calculators, is they used to have these like charts that were square root charts, cube root charts, fourth root charts. Yeah, sine charts, tangent charts. I had to use that when I was in geometry. We weren't allowed to use our calculators. We had to use like the sine, cosine, tangent. So you can create all these charts of values. Okay, so I could look up on a chart what the cube root of 7.8 was. Okay, well, how did they do these charts? They did these with linear approximations. Okay, so imagine you have your calculator and you graph the cube root of x. Have you guys ever done that where you hit zoom, 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 zoom? As you zoom in, this blue line and this red curve look identical. They look like lines. Does that make sense? That's what we're doing. We're zooming in so close to it that we're making our curve look like a line. Okay, and we can always do that. We can always zoom, 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 zoom until we get it. Okay, but we're not actually doing this in the calculator. We're going to do it by hand. So if I have the cube root of 7.8, here's the process that I would do. I find the equation of the tangent line for f of x equals the cube root of x. Okay, so you just told me to find the equation of a tangent line. I need the slope by finding the derivative, and I need a point. What point is close to 7.8 that I actually know how to take the cube root of? 8. So I'm going to use the point 8, comma 2. Because when I plug in 8 to the cube root, I get 2. And I'm going to take the derivative. Well, this cube root of x is really x to the 1/3, right? So as I take the derivative, I get 1/3 x to the negative 2/3. And now I want to find that slope. So my slope at 8 is going to be f prime of 8, right? So I'll call that m. So I get 1/3, and then I have 8 to the negative 2/3. You guys should all know how to do this. That's why we did this before we even started calculus. It was like the first section. So we do 1/3 times 1/4, exactly, because we're doing 8 under a cube root, and then we're squaring it. And since it was a negative exponent, it's 1 over, right? So 1 over the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4, so I have 1/4 there. So 1/3 times 1/4 is 1/12. Okay, so write the equation of the tangent line. Oh gosh. I think I've told you guys about my student that after the AP exam was like, you know, there were a lot of questions that said like find the equation of the tangent line on the test. How do you do that? I was like, oh my god, we've done that since chapter 1. So it's like, oh. All right. So do you guys have this for your equation of the tangent line? So previously I let you leave it like that. Now we're actually going to solve for y. Okay, so we're going to solve for y. We're going to multiply the 1/12 in. So I get 1/12 x minus 8 over 12 is going to be 2/3. And then I'm going to add that 2 over. So what do I get for my number over here? I get plus 6 over 3. So I have negative 2 over 3 plus 6 over 3. So it becomes 4/3. Okay, this is our linear approximation. This is the equation of the tangent line. If I zoom, zoom, zoom so close that I was like on that point and I was really, it looks like a line. If you keep zooming, it looks like this line. Does that make sense? So the way textbooks typically write this is they do like L of x is approximately 1 over 12x plus 4/3. So the linear approximation. So let's go back to this cube root of 7.8 thing. Bill, you with me? So if I want to find the cube root of 7.8, I plug in 7.8 into this linear approximation. And I find it. That's it. Could you do this without a calculator? Yes, you could. Will I let you use a calculator on your homework and test? Yeah. Because, you know, sometimes it takes you guys a while with long division still. You forget those basics. Cole, did you get it without the calculator? Challenge accepted.
So because that point is so close to 8, we can plug that into the tangent line?
Right. Yeah, as long as it's close to it, it's fine.
It was actually 1.99, but...
I got 1.983 repeating.
No, just do the cube root of 7.8.
Okay.
7.9. Oh.
So if we're finding the cube root of 7.8, so do 7.8 and raise the 1/3 power in your calculator. Is it pretty darn close?
Pretty darn close.
1.983. The first three decimals are the same, and then it goes 192,483, right? So it's pretty close. Okay. Next up. So it says there's a somewhat complicated formula. I've already talked about that. I'm not going to even teach you the formula because I think students spend so much time trying to memorize this formula when they really don't need to. You just, every time you see something that says linear approximation, you're thinking, oh, that's a tangent line approximation. Okay. So there's lots of words we're going to use. So notice how number 1 it says tangent line approximation. Look at number 2. What word do I use? Linearization. Same thing. Okay. Linear approximation, linearization, tangent line approximation. These are all the same. Okay, so number 1, so it says find the tangent line approximation for f of x equals 1 plus sine of x at 0, 1. Use this tangent line to approximate f of 0.323. So right now, do you guys know what f of 0.23 is? Like if I was trying to find that, I'd have to find 1 plus sine of 0.23.
Well, 2, 3 is pretty close to the fact.
I don't know, that would be pretty hard, right? So I don't want to do that. I want to find some kind of approximation for it. I want to say, oh, well, it's going to be approximately this. Not 1/4. All right, so we do our tangent line thing. So we take our function and we take its derivative. So what's the derivative of 1 plus sine of x? Cosine of x. That's going to be our slope when we plug in the x value of 0, right? Cosine of 0, 1, right? So we're saying on our unit circle, when I have an angle of 0, I go out to 1, 0. The cosine value is 1. So that's my slope, and then my point is 0, 1. That's the y-intercept, yep. So you could write it as y equals 1x plus 1. Yeah, if you did the y minus 1 equals 1 times x minus 0, you'd get the same thing. So you'd have x, and then you'd add the, yeah, you would. You'd add the 1 over. Yeah, same thing. All right, so the reason I knew I could skip directly to y equals like 1x plus 1 is because 0, 1 is a y-intercept. So I can make that like my y equals mx plus b, it's the b. Does that make sense? So you don't have to do the y minus y1 in that case. Okay, so this is my tangent line approximation. And if you check, if you ever did like 1 plus sine of x, it looks like, whatever. It's like sine of x, only it's been shifted. So it looks something like that. And if you do find a tangent line approximation at this point, it's this line right here. So you can try that on your calculator. You'll see it works. So basically, if I zoom in just in this area, it looks like that line. Do you guys understand what I'm saying? It's really close to 0, right? 0.23. All right, so that's what we're doing. Okay, so now we're not done. So now we're going to use this tangent line approximation to find this x value. So we're going to say, well, f of 0.23 is going to be close to just as if I'd used this function instead. So it's going to be 0.23 plus 1, which is 1.23. Can we do that without a calculator? Yeah, we can. Really easy. And if you check, so if I do 1 plus sine of 0.23, my answer in my calculator says 1.227977524. So it's close to the first 2 decimals, right? Which is pretty good. Yeah. Shh, guys. Alexa?
Will it always like give you the point that you should use for the approximation?
No, sometimes it doesn't. So Alexa's saying, like, will it always give me the point that I should use? No, sometimes it doesn't. So on your homework, you guys will have things that look like this. Like it will say, find the approximation for e to the 0.21. Okay? What function would you use for that? E to the x. What point, like what x value am I close to? 0.21, right? Does it make sense? So I would use, or the 0.21 is what I want, so I'm close to 0. So the point I would use then would be 0, comma, what do I get when I plug in 0 into y equals e to the x? 1. So I'd use 0, comma 1. Does that make sense? So you always pick one that's close to it.
So
Good? All right, so the next one, so find the linearization of the function. So we have f of x equals the square root of x. And we're at the point 4, comma 2. So use this to approximate the square root of 3.98 and 4.05. Are these approximations over or underestimates? Sketch the line and the curve. Okay, so we're going to think about this. So we have our function. It's clear that if I'm finding the square roots of 3.98, right, and the square root of 4.05, I'm definitely using an x value of 4. That makes sense, right? Do you guys see that? So that's why I'm using this point 4, comma 2. So I take the derivative. Do you guys know the derivative of the square root of x?
1 over 2.
Oh, I'm so proud. And then I find the slope with that. So I plug in 4. So I get 1 over 2 times square root of 4,
1 over 4.
which is 1 over 4. So that's my slope. And then I have a point, which is 4, comma 2. So I do y minus 2 equals 1/4 times x minus 4. And I simplify it, right? So when I simplify, I'm going to have y equals 1/4 x. When I distribute the 1/4, I have minus 1. But when I add the 2 over, I get plus 1. So that's my linear approximation. So you can do your L of x is approximately blah, blah, blah if you want to. I would just leave it like that. That's fine. So if I'm finding an approximation for these, I don't go back to the square root because I don't know how to take the square root of 3.98. Yeah?
Will you have to put L of x?
Yeah, the AP graders I don't think would care about that. Hopefully not. Who knows? All right, so the square root of 3.98. So what do? So we go to our linear approximation, and what are we plugging in for x? 3.98, exactly. So I'm going to have 1/4 of 3.98 plus 1. And you can do that without a calculator.
how would you divide 3.98 by 4?
Long division.
I
don't know.
Yeah.
Will I have to do that on a test?
No.
You can.
You know it's going to be about 2.
These are usually multiple choice questions, and they give you, I don't know. I'll show you one. All right, it's clearly about 2. Most of, when it's a multiple choice question, surprise, all the answers are close to 2. So it doesn't really help you. All right, so here we go. So 4.05. So I would do 1/4 of 4.05 plus 1.
So this will be 2.005.
So 2.0125. They're not the same distance away. If they were both like 0.02 away, then they'd be similar distance away, but they're not. All right, so were those close to what we had? So we can find the actual values. You can plug it into your calculator. You can find, well, not really, it's like goes on forever, right? But you find an approximation, and you can decide if it's an overestimate or underestimate. But when the AP test asks you this part is usually on the non-calculator section. You have to know if that's above what you want or below the actual value. Okay, so here's how we do this. We think about the graph. All right, so our picture is 4, comma 2. Every day. I should have them listen to my YouTube videos and hear the background noise. Yeah. Oh, I'm sure you can hear it. You can hear all you guys talking on the YouTube videos, so. All right, so here we go. Every day. All right, so are these approximations overestimates or underestimates? So let's think about our tangent line. Would our tangent line be above the curve or below the curve? Above, why? Because it touches above. Okay, the justification you need on the AP test has to do with it curving downwards like this, like on my hand curving downwards. What's that called?
Concave down.
Concave down. Good job, Alexa. So concave down. When something is concave down, the tangent lines are always above. So if the tangent line is above, those numbers I just found were the points on the line, not on the curve. We used the line to approximate it. Right? So our curve would be close to here. Let me do a real exaggerated one so you can see. So if that's our x equals 4, here's the two values we found. Are they above the curve or below the curve?
Above.
They're above. So are they overestimates or underestimates? They're over. So when something's concave down, you end up getting an overestimate. So it's an overestimate,
So you have to know
the concave down. Yeah.
But if we were
I
like,
mean,
Yeah, and usually it's an easy function to think about. Yeah.
oh, later, one was an overestimate, one was an underestimate.
There could be, I guess. I don't know. Maybe if like you had x cubed or something where it changes like at 0.
Well, I was thinking
Yeah.
like the sine function where x
Mhm.
equals, like the slope equals 1.
Yeah.
Where it's going through the
Oh, that's true.
point of
The sine of x.
inflection.
Yeah. So Nick was saying, this is a good question. He said, is there ever one where like one of them would be an over and one of them would be an under? And I said, yeah, like if something changes in concavity, definitely. And so then Cole said, well, what about sine of x? Because that sine of x one we did, at 0 it would change from concave up to concave, or concave up to concave down. So if you picked a number on the right of it and a number on the left of 0, then they would be different, right? Does it make sense? So you have to think about each scenario. So yeah, these are both concave down. So the justification would be like f double prime is less than 0. Therefore, our approximations are overestimates. Our approximations. Okay, how do we read this? So I was telling the first period class that calculus is a foreign language in many ways. So just like French and Spanish and so on, when you see something like that, you need to know how to read it in calculus. So what does that say? I mean, not f double prime is less than 0. Wow, you guys are super smart. Right. It's concave down. So since it's concave down, then blah, 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 right? Yeah, Alexa.
Was it talking about how the curve of sine of x you might have something over and underestimate? Is that like at a point of inflection? So does that mean
Yeah, like points of like if you use an x value that's at a point of inflection, something on the right of it and left of it might be overestimate versus down. It would, yeah. All right, so use this equation to approximate the square root of 25. Do we all know the square root of 25? It better be 5. But if I'm using that equation that I just found, I said my equation was 1/4 x plus 1, right? So if I plug in x equals 25, yeah, we get 7.25? We get 7.25. Is that close to 5?
Ish.
Not really, because the square root of 25 should be 5. So it's not close to 1 decimal or 2 decimal or even the original like whole part, like 5 versus 7, right? It's not close. Okay, so what's wrong?
Scale of like 3,000.
I need to use a different point because at that point 4,2, that's not helping me with way over here with 25. I didn't give much room. That's even further out than 25. Because see what's happening is we get this equation of a tangent line, and you're going to be way off the further out you are. Does it make sense? So this is why our points have to be really close to the value. So is it close to the actual value? No.
But how could you do that one by hand if you don't have already?
Well, I hope you know the square root of 25 anyway. But if I asked for the square root of 26, what point would you use? 25, 5, right? So no, because x equals 25 isn't close to the x value of 4. Yeah, Nick?
So when you give things like that on the test, I was reading that as like the point was 20, square root of 25, that would be like the x value, then you would plug that back in.
No, if you're approximating the square root of 25, when it says things like approximate the square root of, like if it said approximate square root of 26, you would have to interpret, okay, my function is square root of x. I want the point 25, 5 to be next to it. Okay, so number 3. So find the linearization of g of x equals the cube root of x at x equals 64. All right, so my g of x function is x to the 1/3. So my slope, g prime of x, is 1/3 x to the negative 2/3. So do you know how to find 64 to the negative 2/3? What is it? So the 1 over, the negative exponent makes 1 over the cube root of 64, and then squared. So Phil's our resident expert for fractional exponents. So we get 1/3 times 1 over 16, which is 1 over 48. So that's our slope. So our tangent line is going to be y minus, and then we're like, ooh, we only have x equals 64.
Can you like average out like a bunch of tangent line equations and get is there a way to do that? Like just have like a bunch of people and like and like do something and like get the equation?
I mean, maybe. It's like regression curves. No. All right, so it wouldn't get the exact curve. All right, so your point is 64, comma what? 4, because you go back into your cube root of x. Ari, I took a class in college called Numerical Approximations. You would like that. No, because we weren't allowed to use a calculator, but we had to do things like that. So it was fun.
How many math classes have you taken?
I've taken a lot of math classes. I was a math major, and I went to school,
That's why I
grad
wanted to
school, for math.
Where'd you
know, like
go?
number.
I like when people ask, how many calculus classes have you taken, Mrs. Cox? I've taken all of them. I've taken Calc 1, 2, 3, Advanced Calc,
There's a third
not Advanced Calc, like, what do you call it, analysis. Like, there's tons
Wait,
of
is this
calculus.
top one?
I've taken calculus in complex numbers in grad school. I've taken every calculus.
Where'd you go? Grad.
IU.
Where'd you go for undergrad?
USI, a very small school in Evansville, and I liked it. All right, so here we go. So y minus 4 equals 1 over 48 times x minus 64. Did you guys find your equation? What do we get? So we did negative 64 over 48 plus 4. Yeah, so plus 8 over 3. And so if we're doing the cube root of 65, we're using this linear approximation, and we're plugging in 65. So 65 over 48 plus 8 over 3. So I get 4.0208, 3 repeating. And then this one, so 61 over 48 plus 8/3. So 3.9375. Are these numbers that are close to what you expected? Yeah. So if you're getting something like the cube root of 65 is like 210, you probably did something wrong, right? So you want to think about that.
I feel like it should be smaller.
Mm-hmm. All right, so really quickly, let's go through. So number 4 says find the linearization of the function at a equals negative 1. Whenever it's a equals, that's the same as x equals. Because in the linearization formula, the one that I didn't show you in the book, it uses an a. So that would be the same process. This is just asking for the tangent line approximation. I'm not using it to approximate anything. So for this one, I do f prime of x equals 4x cubed plus 6x. And I plug in negative 1 to get my slope. So I get negative 4 minus 6, which is negative 10. That's m. My point is negative 1 comma something. So what do I get when I plug in negative 1 to the original? 1 plus 3, which is 4. So I get y minus 4 equals negative 10 times x plus 1. So I get negative 10x minus 10, but then I'm going to add the 4 over. So negative 10x minus 6. That's your linear approximation. So if you want to write like L of x is negative 10x minus 6, like something like that, or approximately.
Huh? Does it matter if we use uppercase or lowercase l?
I mean, if you
Not for L's, but it does for F's. All right, so number 5. Do you guys see what you would do for number 5? We're feeling pretty good with this? What would our f of x be? What function would I use, though?
Oh.
Square root of x. What point would I use?
144.
Comma? 12. Exactly, and then you would go through that process. So the thing that I told the last class is I have a lot of weird ones on your homework, and people get stuck on these. So if I have e to the negative 0.12, your function is what? E to the x, and your point is 0, 1. We did that one earlier, something like that. What if I have cosine of 0.17? What do you mean? What's my function?
Cosine x.
Cosine of x. What's the point?
Cosine 0, which is 1.
0, 1. Exactly. What if I have 1 over 1.18?
1 over x.
My function is 1 over x. My point is 1, 1. Exactly. Did you guys get it? What if I have the 4th root of 64.1? Can I do the 4th root of 6? No. Let's do 81.13. What's my function? 4th root of x. What's the point? 81, 3. Good. Yeah, does this make sense? Then you would do all those process, the same process. You'd find the equation of the tangent line, and then you'd plug in 81.13 for x eventually. Does it make sense? Okay. Can we skip these ones? Do you feel pretty good with this? This is an example of one. Number 7 is definitely like an AP question. So let's look at number 7, I guess. So the approximate value of f of x equals the square root of 4 plus sine of x at x equals 0.12 can be found by the tangent line approximation using x equals 0. So find the approximation for f of 0.12. This was a multiple choice question that was on the AP test a few years ago. So you would see that you said something like tangent line approximation. You'd be like, oh, I know how to find tangent lines. I find the slope, right? And I find the point. So this was 4 plus sine of x raised to the 1/2. So its derivative is 1/2 times 4 plus sine of x to the negative 1/2 times cosine of x. Exactly. And you'd say, well, I don't want to plug in 0.12, but I can plug in 0. What point is it at in the original function? 0, sine of 0 is 0. 4 plus 0. Yep, 0, 2. Because f of 0 was 4 plus sine of 0 is 0, I got 2 out, right? So then I would find the slope at x equals 0. So I have 1/2, 4 plus sine of 0 is 0 to the negative 1/2 times cosine of 0. What's cosine of 0? 1. So I have 1/2 times 1 over 4 under a square root times 1. What's my slope? 1/4. So then I have y. It's nice because I have the point 0, 2. Do you guys remember what I told you about 0, 2? That's the y-intercept. So y equals 1/4 x plus 2 is my linear approximation. So that's my like L of x equation, right? So if I'm finding f of 0.12, I can instead use this simplified function. Much easier to plug into this than it was the original. And if this was on a non-calculator question, please help me. I hope you know how to do this. What's 12 hundredths divided by 4?
0.03.
0.03, I agree, 3 hundredths. So 0.03 plus 2, so my answer would be 2.03. Would you be able to handle that without a calculator? Good, because I was on the non-calculator section. Make sense? Okay, so we'll stop there and I'll give you your homework.